Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video on Math Basic Course. And as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on aside as we jump into the Chapter 5 review in the Big Ideas Math Integrated Math 1 textbook. This is everything systems of equations and inequalities as we got into section 5.7 on. In fact, sections 5.1 to 5.4 we did do a quiz review on, and we got a mix of some of the solving systems by graphing, then elimination, substitution, and they forced some on us. They're going to have to force some on us again because we do go by section. So like 5.2 will be substitution, 5.3 will be elimination, etc., etc. So we did solve systems, and then on the back end, we did solve by graphing again, just basic equations, and then we got to graphing inequalities so we could do systems. So all of that together in only 22 questions. I was actually quite surprised to see that only 22 questions, because normally they do about 30 or so, and I feel like they could do a whole bunch, but 22 might lighten the load as an overall. Jump to the description section down below if you'd like to find the PDF for this source material, as well as graph paper PDF and timestamps to each individual problem or section startup, because I do a little preview with the examples that they lead into. Without further ado, I'm going to go ahead and get started with this. We're going to look at section 5.1 on solving systems of linear equations by graphing. Now, leading into this, we already knew how to graph out of standard form, slope-intercept form, all that. Whole point of this basically was find the point of intersection of these lines. So this example, they have a system, two equations. For what x do we get the same y? Single value. Y equals x minus 2 is this line right here, y-intercept of negative 2 and a slope of 1. Y equals negative 3x plus 2 as a y-intercept of 2 and a slope of negative 3, like that. They intersect at 1, negative 1. When x is 1, y is negative 1. And you can double check that. When you substitute 1 and negative 1, it should work for both equations. If it doesn't work for both, it's not a solution to the system. Now, they're not asking me to personally double check. If I do, it'll only be mentally. Outside of that, I'm going to trust my own work for it. But that is the solution to that. And the final solution is written as an ordered pair, not just for graphing, but graphing is a good reminder that that is how we are going to write our answers. So let's begin. We have questions 1, 2, and 3 where we will solve by graphing. Now, just a reminder, section 5.4 was where we had special cases of no solution, infinitely many solutions, so I don't expect them to show up here. So we're only expecting to see one solution and exactly one solution for linear inequalities. So y equals negative 3x plus 1, y equals x minus 7. We'll graph those two. What I generally do is I've been making one of them blue, the other one green. I hope that's okay. Then I'll just do that here and then just find the point of intersection. So wait a second, negative 3x plus 1. Oh, they had negative 3x plus 2. I'm like, isn't that the same graph? It's parallel to it. It's almost it. So I got a slope of negative 3 starting from this y-intercept of 1. Negative is down and right and also up and left like so. You still do everything that I would do here. Plot as many points as you can fit, draw a line with arrows, and then seek the point of intersection thereafter. This is, after all, solving by graphing. We have algebraic methods we'll do after. So there's one of them. The one in green I'll do is y equals x minus 7. Yes, that does mean I'm going to be plotting up 1 over 1, even after I just found the point of intersection there. Now, I'll just speak out loud in this stuff as I have an opportunity to. Graphing has a nice visual representation of what you're doing, what the point of intersection means, as well as when we have no solution or infinitely many solutions, what it means there. So I like it for that reason. I love graphing systems of inequalities with word problems. You guys probably know that from my section 5.7 video. So there are some great needs for them as they exist. Of course, solving algebraically also has its needs, and we'll be talking about those, because graphing has its drawbacks as well. So this is an ordered pair that is 2, negative 5. That should be the solution to this as a double check. When y is negative 5, negative 5 equals negative 3 times 2. Negative 6 plus 1 is negative 5. And 2 minus 7 is also negative 5, which equals that. So that does pan out. That is the solution. Number 2, we have a slope-intercept form equation, and then one in standard form, which I believe I'm going to put in slope-intercept form. And that's because that x-intercept would end up being a fraction. I don't like dealing with fractions unless they're a slope, which I think is what we're going to have to do. No, actually, it won't be a fraction slope. But 4x minus 2y equals 6. As a rewrite of this one, let's subtract 4x from both sides, and then we'll divide everything by negative 2 on that equation. We get positive 2x minus 3. So negative 4x plus 3 and positive 2x minus 3 are our two equations we're going to be graphing. The first one I'll do blue. Second one, as you can tell, I'm going to make green. It's not easy being green. Got to put things in slope-intercept form, things like that. So negative 4x plus 3, looking a little bit down 4 over 1 like. Right here. Now again, my line tool has pre-made arrows, so don't forget to make your own arrows as a result of what I'm doing there. 2x minus 3 is here, up 2 over 1. There's our point of intersection. You know, one of the drawbacks of solving by graphing, this isn't true for this one, but what if they intersect at fraction values, decimals, irrational, well, not irrationals, but values that you can't really tell where they're intersecting. So that's always a fear of these kinds of questions. Didn't really seem like they gave us any that way. I think they were very nice and comfortable and are giving us ones that we'd be comfortable with. We can find an integer point of intersection like this. So that would be one of the things we'd have to worry about. That's not the case here. This intersects at 1, -1. If you do a substitution, that should pan out. Yeah, it should pan out right there. That's all good. Number 3, and I'll keep speaking on other drawbacks. Other drawbacks would be, hey, what if your graphs are, you know, out of window range? Not only are your x and y intercepts something where you have to change your scale maybe, but maybe where they intersect would be out of window range as well. Or you do have a y-intercept that's a fraction, something like that. So I'm not poo-pooing solving by graphing. I'm just saying if I have another method to choose and it's kind of ready for me, like I can use elimination method here pretty well as well. I'd love to do that. Now with this one, solving by graphing, guys, I'm going to go ahead and treat these as graphing the intercepts here. I got an x-intercept here of 3 and a y-intercept of 3 if you divide those by 5, the coefficients. And here we get an x-intercept and y-intercept of, well, 5 for the x, -5 for the y. 2 points can make a line. We've done plenty of graphs that way, so I'm going to go ahead and do it here. Can you see the whole thing? You can see enough. Okay, so for this one, x-intercept of 3, y-intercept of 3. I was almost for a second thinking these are going to be parallel. Oh boy, I thought we weren't seeing that until 5, 4, but they're not parallel. The other one's +5 and -5. Now, you really want to use a ruler if you're using standard form on these ones, because I'm not plotting as many points as I can fit. I'm just maintaining kind of that slope of -1, which is what it is. Down 3 over 3 is also down 1 over 1 when reduced. 5 and -5 are right here. And I've stated this before, but the farther apart they are from each other, the more precise you're going to be able to be with your line in general. So with like, if the x and y-intercept were 0, you'd probably have to do slope-intercept form. If they're 1 and -1, I would caution you using standard form for that same reason. But if everything went to plan, and it looks like it did, we are crossing at that point of 4, -1, which is the point of intersection there. X is 4, y is -1. We always write ordered pairs of these solutions as these solutions when we can. And you can double check it. Should be good. All panning out. Okay, that was section 5.1 in a nutshell, solving systems by graphing. Now we have 2 algebraic methods to look at. 5.2 on solving by substitution, and then 5.3 on solving by elimination. And using that in a little bit of 5.4 as well. So section 5.2, let's keep this on the screen while we're doing it. Solve by substitution. This method is all about isolating a variable, make it say y equals somewhere or x equals somewhere, even if it has the other variable in its expression, totally fine. Our goal is to substitute that expression into the variable in the other equation, so we have one equation with one variable on it. Case in point, I have a system right here where I could get this y by itself or this y by itself. They decided to add 2x to both sides, get that y isolated, and now I have this 2x minus 8 expression that I can substitute for y in the other equation. You got to use the other equation because you got to use it in a way that's going to interact with the system. For what value of x does it kind of work with in that way? So when it plugs in for y right there, you can see now you have one equation with one variable just with x's and use it to solve for x. They do their things, combine like terms, add 8 divided by 9, they get x equals 2. Now they wouldn't be done in that set yet because they still need to solve for y. Just like solving by graphing, there should be an x and y ordered pair. Don't be done at x equals 2. Now, when you substitute 2, they say into an equation 1 you get y equals -4. I would even personally prefer to substitute it into this one right here. 2 times 2 minus 8. Boom, right there is where I'm going to be doing that substitution. You also get y equals -4. So 2, -4. 2 for x, -4 for y is that ordered pair. As if I graphed those two, that's where they'd intersect. And not as if, like that's where they would. But that's kind of the point of it. Okay. So we have numbers 4, 5, and 6 to solve by substitution. Number 4 is a little bit more leading for you because one of the equations already has a variable isolated. The bottom equation got a y all by itself here. Y equals 5x plus 7. And listen, I won't be precious about it here. They really do try and lead you into using substitution when you should for these ones, meaning something can easily get by itself without cause of fractions, so they're not trying to hurt you in the process. That's kind of nice. Anyway, in substituting here, now this equation on top will say 3x plus y, which is 5x plus 7. That's substituting there, equals negative 9. 3x plus 5x is 8x, and the 7 does not combine. In fact, let's subtract it over. Let's get 8x is negative 16, and divided by 8, we get x equals negative 2. I've stated it the entirety of the chapter. I am no longer showing actions on how I'm moving things over. The book doesn't do it either. You can tell they're not saying, hey, divide both sides by 9. They cancel out. We're not doing that anymore. My earlier chapters, I've been doing it. No longer. We're going to go for efficiency's sake, and I hope you push toward it as well. Where it says y equals 5x plus 7, that would be my favorite place to substitute for this x because that y is by itself. You could do it in the top equation and you should get the same value, but for simplicity's sake, I'm going to do it right there, and I get negative 3. So negative 2 for x, negative 3 for y. There's our solution. It is an ordered pair that we write ultimately. We're good. So, solving by graphing maybe won't be my preferred as an overall, but it does remind us that we need to write our final answer as an ordered pair. And if you forget it when solving using these other methods, don't. It's specifically that x with that y that works for both equations simultaneously. Oh, it did say check your solution. Let's just double check it. I'm going to do it mentally, though. So when I substitute it, I'm doing it in full. Like negative 3 times negative 2 is negative 6. So I'm going to say negative 6 minus 3 equals negative 9. And this one we kind of already checked because we literally did that substitution. So I'm just checking the other one. It seems to work. Okay, number 5. This time we have no variable isolated. So you make a choice. Would I like to get this x by itself, this x by itself, or this y by itself? Why not this y? I'd have to divide everything by 4 ultimately, which leads to fractions. It's not impossible, and it's not wrong if you do it. It's just ill-advised. Strategically, I wouldn't go for it. Personally, I'd like to get this bottom x by itself. I'd like to I'd like to add y over and get x equals positive y plus 1. It took one step. Everything is positive there, and when substituting into this one, where I take this y plus 1 and shove it up your x. Sorry to the headphone users. When I do that right there, it's a simple substitution, no distribution, anything like that. Sometimes we will have distribution, like if I did it for y, etc., etc. So here, when I substitute it, it'll now say y plus 1 plus 4y equals 6. Y plus 4y is 5y. And subtract 1 from both sides and divide both sides by 5. You get y equals 1. Now we're not done. We still have to solve for x. Very simple. And this is, like I said, in substitution method, what I love about this is x is already isolated once. 1 plus 1 is 2. And there you have x equals 2. So 2 comma 1 is your ordered pair. If we do a substitution, and I'll check it with the top equation, because the bottom equation we just kind of checked it with. 2 minus 1 is 1. 2 plus 4 is 6. Very easy check. Very, very quick check on these things. Now this next one, like I stated, something very leading for us. If we had to pick and choose, you're looking at the equation as I write it. If we had to pick and choose which variable we'd like to isolate, the top x, top y, bottom x, or bottom y, which would you go with? Clearly, the one that takes one step to solve and leads us with no fractions, the bottom y. Subtract 3x from both sides, we get 6 minus 3x. So that's where I'm going to go with that. So I'm going to substitute this in for the y up here. Now, that does come with distribution. That's okay. It still is the easiest go-to for it. So rewrite the top equation, but instead of y, I'm going to rewrite that as 6 minus 3x. Use parentheses, right? That's a substitution. So now we're going to distribute 3. Combine like terms here. Subtract 18 and divide by negative 7. We should get x equals 2. When you substitute 2, once again, I'm going to use this equation here that I did the rewrite for. 6 minus 3 times 2. 3 times 2 is 6. 6 minus 6 is 0. So you have 2 comma 0 as this ordered pair, and we have done successful substitution solving, y'all. Oh, we have a word problem down below. Let's double check this before we move forward. 4 plus 0 is 4. I'm doing substitution. 0 plus 6 is 6. Okay. Number 7, word problem. Now we have to come up with the equations for the system on this one, it looks like. You spend, and these are equations, not inequalities, right? My favorites, the inequalities. You spend, I'm not being sarcastic, I love them. You spend $20 total on tubes of paint and disposable brushes for an art project. So you spend them on tubes of paint, you spend them on disposable brushes. Got it. Tubes of paint cost $4 each and paint brushes cost 50 cents each. You purchase twice as many brushes as tubes of paint. How many brushes and tubes of paint do you purchase? So this is one of those things where, and I'm going to type it out. I'm going to use not X and not Y just because I can here. We're not graphing, and T and B I can write without looking like any math symbols. I know T can look like pluses to people, but if you curve it, you're good. T will be, oh, actually, let's use P. P is number, how many? Number of tubes of paint. P for paint. And B is number of disposable brushes. Okay, so with that in mind, 2 equations we can write. A dollar amount, okay? The cost of each tube of paint is $4. Cost of each paintbrush is 50 cents. So this is how much money I spent on paint. Excuse me, what was this? Just brushes. Paint, tubes of paint, and brushes. This is how much money I spent. Dollars plus dollars equals dollars. So I spent $20 total. Now there's a comparison equation. You purchase twice as many brushes as tubes of paint, as if to say the number of brushes is twice the number of tubes of paint. Don't confuse the two. You don't double the B, you double the P, if you will. More brushes than there are tubes of paint. So that's our system. In this system, we can substitute. Solve by substitution. B equals 2P. 2P can take B's place right there. So I can make an equation that now says 4P plus 0.5 plus 2P. And that's a nice multiplication. That becomes 1. 0.5 times 2 is 1. So 4P plus 1P equals 20, or 5P equals 20. Divide by 5, you get P equals 4. Now, solving for B is kind of the same, is twice as many brushes as there are tubes of paint. So B is 2 times 4, or B is 8. So that's the answers. Now, the other reason I can use, see, we're not graphing them. Our answer is also not an ordered pair this time. I said always write it as an ordered pair, not for word problems. So in a word problem, write it contextually, right? What is the question? How many did I purchase? I purchased 4 tubes of paint and 8 disposable paint brushes, or disposable brushes. So that's my answer there. It's not an ordered pair, so, the X and Y doesn't really matter for me there. Okay, guys, that's the substitution method. Hope it's making some sense. We're probably going to revisit it when we go to section 5.4. At least we have the opportunity to, when all said and done. Let's go to section 5.3 on solving systems of linear equations by elimination. Now, using elimination is adding down the list. Look, you want a lineup of things. I've said it before, but you want to line these guys up, equal signs, variables, and constants, things like that, and you can add down these lists due to equivalency and balance of equations. And if a variable eliminates along the way, all the better for it. If I added down these lists right now, nothing would eliminate. I'd get 5x plus 4y equals negative 10. So what I need to do is manipulate one or both equations in order to eliminate something. For example, you could multiply the bottom equation here by 3. That would eliminate y's when you add 6y minus 6y is 0. Boom. Those would eliminate. That's what you're seeing right here when you add down the list. So now you have an equation with just x in it to solve for. Now, did I have to solve for y by multiplying by 3? No. I could have solved for x by multiplying by negative 4. Do I prefer that? No. It's a bigger number and it's a negative. That means there's more error involved, possibly. If I get additive inverses here easily by multiplying by positive, I'm going to do it. So I agree with them. I'm going to multiply this whole bottom equation by 3. And yes, that includes the right side of the equation. Don't forget that. So 7x equals negative 14. Divide by 7x equals negative 2. Generally, elimination method only means using it in that first moment. We don't use it thereafter. Generally, we just use substitution after that. If x is negative 2, take that negative 2 and shove it up your x. Take it and replace it in one of your equations of choice. The one part elimination doesn't have over substitution is in the substitution method. Normally you get a variable by itself. It would now say y equals something, and I'd love to plug in that equation Here you got to do some extra work to get there. It's not the worst thing in the world. But substitute -2 for x, and you end up getting y equals 0. So this ordered pair, like with substitution, is -2, 0. So we got 3 problems to do here. Looks like no word problems on this set. Let's start with number 8. We have 9x minus 2y equals 34. And 5x plus 2y equals -6. Now, right off the bat, through addition, the y's here would eliminate, so I'm going to go straight into that. Boom, elimination, as everything's lined up otherwise. So, as these y's eliminate here, you're left with 14x equals 28. And keep in mind, we are adding down these lists. We treat the signs as they are. Positive plus positive is positive. Positive plus negative is subtraction. Sorry, positive plus positive is adding. Positive plus negative is subtraction. I'm just treating the signs as they are. That's why these cancel. They're additive inverses. Divide both sides by 14, you do get x equals 2. Let's go and substitute that into an equation to solve for y. I'm going to go and choose the bottom equation here, where I have 5 times 2 now, 5x, plus 2y equals -6. If I subtract 10 over and divide by 2, I get y is -8. So an ordered pair, the ordered pair is 2, -8. They say check your solution. I don't know if I remembered to check all my solutions in the last set, but I kind of just checked with the bottom. Let's check the top of 18 plus 16, and that's 34. Okay, number 9. Number 9 doesn't seem to have the luxury that number 8 has. We probably have to follow more so the example. And keep in mind, if you'd like to see more problems with these, not only do they exist in section 2.3, but we had a few of them on the quiz, on the 5.1 to 5.4 quiz. And it looks like these are going to fall into the same way as the quiz ones did, which is a little more progression as we go. Here, we can take one of these equations and multiply by something like, I could multiply the top equation by -2, that would eliminate x's, or the bottom equation by +2, and that would eliminate y's. I'm going to go for the bottom equation with +2 just because it's positive. That's it. There's no other reason. Multiply by +2 and I get 4x minus 6y equals -38. I'm now kind of ignoring this equation right now as I want to lead into adding down this one with this one here. So the 6y minus 6y will eliminate, and you're left with x plus 4x and 28 minus 38. Divide by 5, you get an x value of -2. Very nice that they haven't, as I mentioned with solving by graphing, if you had some fraction answers, they'd be hard to determine. Here, algebraically, we could easily determine it. However, it's nice to not have so many fractions in the way. So far, nothing really. I'm taking the top equation, substituting -2 for x here. Add 2 to both sides and divide both sides by 6. You'll get y equals 5. So I have an ordered pair of -2, 5. Now, I have mentioned, and it's been apparent, that once again, we don't use elimination for the second variable very often. I could have still multiplied the top equation by -2, eliminated x to solve for y, gotten 5. We tend to use substitution. I think it's faster. Personally, I can't think of many times where getting the x's otherwise would be faster, or solving the other variables faster by using elimination twice. Once is good. Substitution after is great. All right, 8x minus 7y equals -3, and 6x minus 5y equals -1. Here's that progression into the hardest of types here. As I would add down these lists, nothing would eliminate, but also there's no integer I can multiply by, say on the bottom equation, to make a multiple of these coefficients on the top equation. So in terms of eliminating a variable, one, make a choice, and there's not necessarily one better than the other, but I will. But here's the other thing, you probably got to manipulate both equations. So with 8 and 6, I see a least common multiple of 24. That's smaller than their least common multiple of 35, plus there are negatives involved. Let's just deal with eliminating x and solve for y. So being 24, you can multiply this 8 here by 3 and the 6 by 4. What I'd like to do, though, is make one of them negative as well. So if I multiply this, say, by -3 and +4, maybe it'll pan out for me. So let's rewrite these two. What you're now going to see is a -24x here plus 21y equals +9. Be careful on that distribution. And a +4 here, you get +24x minus 20y equals -4. I was thinking hard about this one and saying which one will make it positive, and this makes it great. Not only do these eliminate, this actually gives you y straight up, y equals 5. Hey. So we got y equals 5 here, and we can take and substitute for y any of these equations, do I want to use a big one? Nah, let's use a smaller one. Let's use this bottom equation. 6x minus 5 times 5 is negative 1. Add 25 over, you get 20 fout. Divide by 6, you get fout. Fashout. So 4 comma 5. And that was with the bottom equation, so let's double check with the top. I probably skipped double checking on the last question, but we get 32 minus 35, and that is negative 3. All right, that's some elimination, and like I said, we might be seeing it in this next section, because section 5.4 is solving special systems. And in solving special systems, it's basically ones that have no solution or infinitely many solutions. Maybe, just maybe, they might still have the one solution things. We did see that on the quiz. We did see that in the section. So they do throw you those in the fray. When we hit the chapter test next, I hope they don't kind of warn us when there are possible no solution, infinitely many solutions. That's what I'm most excited for when it comes to something that's most test-like. Now, before we start number 11, let's take a look at this example. Looks like they're going to go substitution method, and I would agree because y is isolated here. So they're going to have that replace y up in here, and they're going to try and solve algebraically. So when they try and solve algebraically, they plug some things in, but 4x minus 4x cancels out, and you're left with a statement that says negative 12 equals negative 14, as we know is not true. Now, we've run across these kinds of equations as early as chapter 1, so it's not new to us to say, as long as the math's right, when the left side doesn't equal the right side, not a true statement, it's a no solution case. And that's exactly what this is. Now, we're not graphing these equations. Well, you could, and if it seems best for me, maybe I will. But we're not graphing these equations. Graphically, what this means is these lines are basically parallel, where you'd have this line here, this line here. They basically just never intersect. There's no solution in those cases. There's also infinitely many solution cases, as we understand it. That'll probably be when the left side equals the right side after variables cancel. So I'm expecting variables to cancel in these cases. Just get ready for those. And we get to choose a method. So in solving this system, and there's really no double check, right? We can't plug in a solution set in these cases here, so we just treat them as they are. All right, I'm going to substitute in here for x. There's something I personally would have done as well here. I probably would have divided this whole bottom equation by 3 or negative 3. But let's just do a straight substitution of x into there and see what we got. So negative 3 times y plus 2 plus 3y equals 6. Distribute the negative 3. And take a look as we combine like terms. Negative 3 plus 3 is negative 3y plus 3y is 0. So you're left with an equation that says negative 6 equals positive 6. Now, that's not true. In absolute value form, sure, we're not dealing with absolute values right now. Not a true statement. This is a no solution case. Make sure that you don't discard that negative sign that was in front of that 6 accidentally or intentionally just because you wanted something to match up. If it's a no solution case, it's a no solution case, and that's exactly what this should be. Number 12. Number 12, I'm seeing this more as a, I'm seeing more elimination to be had, but I want to show you what I want to do with this one here personally. So 3x minus 6y equals negative 9. Negative 5x plus 10y, whoopsie, equals 10. That's a little off the fray there. I'd like to solve the puzzle, Alex. I would like to, okay, as we add right now, nothing would eliminate. There's nothing I can multiply 6 integer-wise by to match 10 or 3 integer-wise by to match 5. So we have to manipulate both equations, and we will. But I'd like to, instead of multiply, I'd like to divide. These can all divide by 3. These can all divide by 5. I think that just kind of, I think it works out better for me to make numbers smaller, and I think it'll really help us to do so as well. This becomes 1x minus 2y equals negative 3. If I divide all these by 5, and right now my goal as I look at this is, hey, this will turn this into negative 1x, which means those will cancel, right? Eliminate right there. Perfect. So now divide this by 5, I get 2y. Divide this by 5, I get 2. But take a look at this. Even the y's eliminate as well. X's, boom. Y's, boom. We're left with 0. Don't forget, that is a 0. Negative 3 plus 2 is negative 1. So all the math was right. Variables canceled, right? That's part of the special cases that we expect here. 0 doesn't equal negative 1. So this is much like number 11. This should be a no solution case here. So notice what I did do in recognizing that I have not only seeking, a common multiple of some sort, that I could do division as well as multiplication. And that's a big go-to that I always like to try and do when I can. Make numbers smaller. I think you'd agree. Just not fractions. Number 13, we have negative 4x plus 4y equals 32. And we have 3x plus 24 equals 3y. Nothing immediately screams substitution or elimination in either case. However, I'm going to go with substitution this time. Now you might say, what are you substituting? Nothing's by itself. I'll get something by itself. I can divide the bottom equation by 3. That'll get y by itself here. Divide this by 3, divide this by 3. It's just like slope-intercept form. Heck, I could graph this if I wanted to. I'm not going to, but I could have. So x plus 8 can take y's place in this top equation. Let's do that. Good old substitution case. Negative 4x. Again, one of these things I could divide everything by 4. Not gonna. Heck, we could have done that, right? We could have done subtraction of 3y, divided everything by 3 and everything by 4. I think that would have taken longer, personally. I don't know. But we're at the stage now where we combine like terms, and those like terms get rid of each other. We have a statement that says 32 equals 32, which is so true in life, guys. That is one of the truer statements I've ever seen. Now, this is a case of infinitely many solutions, and don't confuse this one with all real numbers. This states that these equations are the same line. As I've kind of stated through that example problem, no solution means parallel lines. They never intersect. Infinitely many solutions means they always intersect because it's one line right on top of the other. So it's not all real numbers because I can't plug in anything. I can't just plug in 1 for x and 2 for y, and then boom, it's going to equal 32. But whatever works for this equation, like 0 and 8, for example, will work for this equation. Plug in 0, plug in 8 there, and it'll work. So whatever works for one works for the other because they are the same line. That's how that goes. Okay. That's section 5.4. Let's go to, we have 3 more sections to do. 5.5 was solving by graphing. Now this, whoops, I don't need to write 5.5 here. Now this does bring us back a little bit to 5.1. The difference in solving by graphing here is small. We have to create a system of equations, and our solution that we find is just the x value, not the point of intersection. Case in point, take a look at this. We have 3x minus 1 equals negative 2x plus 4. By the time of section 1.3, I believe it was, we already learned how to solve these in full algebraically, which I could if I added 2x to both sides, added 1 to both sides, and divided both sides by 5. I get x equals 1. Boom. But we're going to solve by graphing. In solving by graphing, we're going to set y equal to this side here, y equal to this side here, because we're finding out what value of x makes the left equal the right, would give us the same y. So if we make y equal both of those and graph them in slope-intercept form as they were, that point of intersection would find what value of x, 1, remember I mentioned that, gives you the same y value of 2. Now we don't care about the y value of 2 because the original equation doesn't have y's in it. Our double check will show that when you substitute 1 in both these, we'll get that 2 that matches. That's fine. But in the case of this, we're trying to see what x value works, and that x equals 1 is the answer. Not 1, 2 this time, not in ordered pair. So it's interesting because it wasn't a true system of equations, but we made it one, and our solution isn't written as one either. So there's that. We'll still use it. Kind of still back to 5.1 stuff from before. So we're going to make a system out of this one, where I'm going to make y equals 1/3 x plus 5. By the way, I'm not bothered by that fraction because it is a slope. And y equals negative 2x minus 2. And let me get a graph axes set ready. Copy, paste. Let's get it started in here. As the Black Eyed Peas once said. As Fergie once said. All right. So this blue one is here. Normally I would do like a double check. They say check your solutions probably, yeah. Normally I would do an algebraic double check and I'd say, okay, I would do this to both sides and all that. You'll hear me do it in the actual section itself. Because it's a fraction, I'm less wanting to do it. But this is the same kind of thing. Like I said, find the point of intersection here. It should be a nice one. There it is right there. Now what we are seeking though is the x value. What x value gives us the same y? Not specifically the point of intersection, like the ordered pair. So when we find that point of intersection, we're just going to say what x equals, okay? So this will be x equals negative 3. X equals negative 3. That's our answer. If you'd like to double check it, let me write it better. If you'd like to double check it, we would plug in -3 for x here. A third of -3 is -1 plus 5. And this is -2 times -3 is just 6 minus 2. -1 plus 5 is 4. 6 minus 2 is, 4. And those check out to be the same. I'm probably not going to do many double checks here. Hope that's okay. But there's that. Now, numbers 15 and 16 you see bring back absolute values. These are not unlike things that we've done before algebraically, even on absolute values on both sides. What I do want to stress, however, is that these absolute value sets will not create extraneous solutions. There may be some no solution cases, but they will present themselves. Nothing through a double check we'll need. Just nothing extraneous as long as it's absolute values on both sides with variables on both sides there. So the x plus 1 either needs to equal the positive version of this, and I don't mean turn these positive, I mean treat the signs as they are, or the x plus 1 needs to equal the negative version of this, which is flipping those signs essentially. Now, what this means is we have two different systems we're going to be devising here. One of them is this one, y equals x plus 1 with y equals -x minus 9. And I did a little bit of cheating on my own, meaning a lot of copying, pasting stuff, so you're going to have to pause to keep up with me on some of this, if I remember my flow. Distributing this negative will turn into a positive x plus 9 on that one. So get ready as I do a little bit of, like I said, little quicker actions for myself because I have to do two different sets of graphs here. I guess you do as well if you're doing the problems. And keep in mind, we are not, and I stated this a lot in the section at the time, we are not graphing absolute value equations. We're solving an absolute value equation by graphing, but we've created systems out of them that are no longer absolute values. So here's what I'm going to do. I'm going to take this x plus 1, because it exists in both systems. Once I graph this first one, I'm going to go ahead and copy it, paste it over. That's not the full extent of all the copying, pasting I'm going to do even. I have one more thing to do, which is awesome. So right here, this guy as a line looks like that. I guess I don't actually need this graph because I'm just going to copy and paste it in a second. So let's copy and paste that thing over. Nope, let's copy and let's, this isn't working. Copy. Paste. There it goes. Oh my goodness. Okay. Time saver. Not really. All right, so same x plus 1, right? Now, let me lock this in place because I'm about to graph y equals -x minus 9. And if you notice, y equals x plus 9 is literally just, it's some sort of opposite of it. Now, the opposite that we're talking about is a reflection in the x-axis. It flips over vertically. And that's what I'm about to do here. I'm about to take this one, copy and paste this line over by flipping it over vertically. So, if you'll excuse me, I'm going to group that, copy it, paste it, thank you, flip it over in such a way that now the slope changed, and I'm going to place it on the right y-intercept for that to change as well. I think something just went wrong, though. I might need to pause my video and reset. Let's see if my pen tool comes up. Yeah, when this happens, this happens. The thing corrupts itself with so many memory issues. Anyway, those are the two equations, right? I'll finish this problem, then I'll pause, which means nothing to you. So, what's the point of intersection on this one? Point of intersection has an x value of -5. If you notice, my pen tool doesn't show up anymore, and this is a big annoyance for me. It's actually hard to work off of. This one right here, they don't intersect. If you notice, these lines were actually parallel. This is a slope of 1 and a slope of 1 with different y-intercepts. That means this one has no solution. Does that mean I write no solution? Of course not. I have a solution of -5 right here. If I didn't have a solution of -5 here as well, I guess I'd write no solution. And it's possible for absolute value equations to do that, but not so much here, right? So x equals -5 is what we're going to go with. That's the answer. We're all good to go. Let me pause this thing just to fix my own software. Hold on. All right, guys, with all that pausing, did you catch up? Yeah, I'm not sure. All right, so x equals -5, just the one point of intersection there, okay? No other set. You can double check it. It should work out. Okay. Number 16. Excuse me. More of the same. More of the same. I expect two solutions on this one. We'll see if that happens. absolute value of 2x minus 8 equals absolute value of x plus 5. See, the thing that made the one solution, or the thing that made that no solution part, is that you had parallel lines somewhere. This one with the slope of 2 and slope of 1, or negative 1, as it's going to be on one of these, will not give us that possibility. So this either equals the positive version of this or the negative version of this. Okay, so in this case here, we'll have a system that states y equals 2x minus 8 and y equals x plus 5. We're still solving by graphing. Now look, we can do this, mentally. Subtract x from both sides, add 8 to both sides, x equals 13. Oh shoot, that's out of our window range. Okay, I might have to change the scale. Well, that's something. Add 3 to both sides, add 8 to both sides, and divide by 3, you get x equals 1. So I'm expecting x equals 1 and x equals 13. Probably good I did a double an algebraic check on that beforehand, because we're going to be outside of the window range on x equals 13. Trying to think of what I want to do now. Y equals 2x minus 8, and y equals negative x minus 5. You know what? We'll just extrapolate. We'll do the best we can as far as our rise over run stuff. I hope you're okay with it. It's going to go a little out of range. We're just going to deal. I'm not going to change scales for this one, unfortunately. I'm kind of stubborn that way sometimes. Especially when I get an x equals 1 answer, I don't want something to look like a fraction when it shouldn't. So, one of the drawbacks to graphing, unless you have accurate scales to these things, or your test makers, your teachers, whatever, have that stuff in mind, yeah, just be careful. So, 2x minus 8. Now, I'm going to do this here, but I know I got to go even farther off the graph than this. This is going to go pretty far off, actually, guys. Oh, I don't know here. If it's going to intersect at 13, it's going to go way up here. I don't know if this is going to be accurate anymore. How close does that look to being? There's my x equals 13. 10, 11, 12, 13. Let's see. Let's see if at least the line holds up. Let's first make our line. And by the way, I'm going to use this for both systems. Ooh, it curves away a little bit. I'm not that good at bringing that about. All right, well, I tried. So we're going to take this one here. I'm going to copy and paste that one. Sorry about that. Oh, don't do this to me. Come on. I hit copy. Control C. I promise I hit Control C. Did it register? Control V. There it goes. Okay. So here's the thing. Let's do the right one first, just because we know that that's going to intersect at a better place. So right here at slope of negative 1, boom, is right there. And we get x equals 1 as expected, as promised. So here we have, boom, x equals 1. Getting my pen stuff set up. Oh, that's the line tool. That's why I couldn't find it. All right, x equals 1. Now let's find that other one. This is going to be y equals x plus 5 as a line. This is where it goes up 1 over 1 until it reaches it. So here's where we really go off the map. It wasn't just x that goes off the grid, it's also y's. So it goes boom, boom. Okay, let's see, pretend like that was 12, I guess. What if I went up 2 over 1? So I got to kind of peter out a little bit there. And then boom, boom, boom. I guess boom right there. So that's 10, 11, 12, 13. So boom, there's the point where it finally hits. Not the best version of it, and I won't say I cheated, but I did anticipate the answer beforehand because I did solve it algebraically. So say what you will out of it. That is terribly done. Say what you will out of it, but that's where they intersect. We solve by graphing, right? So if I did change my, maybe I should have. If I did change my scales, then I would have gotten that x value there. You can double check them. Those should be good. We did check them algebraically, right? But double check by plugging them in. Okay, that's the end of section 5.5. Let's go to sections 5.6 and 5.7, which both feature inequalities. Now, 5.6 is basic inequalities, two variable, but one variable for problem 17, but single equation, inequality. And then systems of inequalities for 5.7. So take what we will out of this and learn it. So this had to do with the shading of a region. They call it a half plane. They'll probably say that somewhere. They use the shading of a region to represent all your solutions here. It's no longer a y equals equation. We graph a boundary line as if it's y equals, or as if it's the equation as is. So y equals negative 2x minus 3, right? That's this boundary line right here. Now, we use a solid line versus a dashed line when we include greater than or equal to the thing, just like y equals, we use a solid line. Otherwise, it's dashed if it just said greater than, for example. Now, how do we know whether to shade on this side or that side? Shading on this side means every point on this side is a solution to the inequality, that when I plug in points such as 0, 0, which they used, which is a wise choice, plug in zeros, these turn into 0, it makes a true statement. So if 0, 0 makes a true statement, then anything on this side should make a true statement. That's just how they work. If I plugged in 1, 1, it would work, or 2, negative 5. Actually, 2, negative 5 would be fine. If I substitute negative 2, negative 5, it wouldn't work in this original inequality, and so nothing on this side would work as well. Another neat trick is if you get y by itself in the inequality and make it say y is greater than or equal to negative 2x minus 3, a greater than in that scenario means we should be shading above the line, which this is above the line. If it said less than, we would be shading below. So I will do some 0, 0 tests, I'm sure, but at some point, especially when we hit the second phase of them, section 5, 7, I'm especially probably just going to be saying shade above versus below, or do a very, very quick mental test. Number 17 on y is greater than negative 4. Let's go ahead and get graph axes back, because all the rest of these are graphed now, guys. It's what they are. We have infinite numbers of solutions, and the graphs are the representations of those solutions. So first I'm going to graph y equals negative 4, which is a horizontal line crossing through negative 4 for y, like so. Y is greater than negative 4 represents everything that's above this line. That means negative 4 doesn't count, so we use a dashed line to represent that. That's what that looks like. And then we do a shaded region. Now I'm going to use my rectangle tool for this one here. Give me a second. I'm going to shade everything above this. How come? Because the y's need to be greater than it, greater than negative 4. If you test a point like 0, 0, this would also show up. Because y is 0 here, 0 is greater than negative 4. Don't even worry about x, no matter what x is. As long as y is greater than negative 4, it works. So these are all of our solutions for number 17. And that's number 17. Number 18. Number 18, we have negative 9x plus 3y is greater than or equal to 3. My personal preference for this one, because the x-intercept would be a fraction, is to rewrite this in slope-intercept form, and I'll go ahead and do exactly that. So I'm going to add 9x to both sides, and I'm going to divide everything by 3. Now, the inequality would have flipped if I divided by a negative number, which I did not, so no flippage, which is where testing a point like 0, 0 is really nice to do in situations like that, because you're really not sure which way it should go. So y is greater than 3x plus 1 means we will be drawing the line y equals 3x plus 1, like so. Because it's greater than or equal to, the or equal to means that this line that we draw will be solid. Okay? Not dashed. That means the dashed line means points on the line aren't solutions. Solid line means points on the line are solutions. Now, greater than means I should be shading above this line. Now, I will go ahead and initiate that shading, but just as a swift reminder here, I can substitute a value, an ordered pair such as 0, 0 for x and y. Now, if I substitute 0 for y and 0 for x in here, I get a statement that says, and by the way, don't do it on the newly written inequality, do it on the original. I'd get a statement that says 0 is greater than or equal to 3. That's not a true statement. Now, 0, 0 is not on the, it's close, but it's not on the side of the boundary line that has the shaded region stuff. If 0, 0 doesn't make a true statement, then no point on this side of the shaded region of the boundary line makes a true statement. Therefore, these aren't solutions, and these ones are. So I tried 0, 0. It didn't work. Therefore, the greater than made sense here. Y is greater than does mean you shade above the line, though. So that's what I did, shading above the line. Number 19, 5x plus 10y is less than 40. I'd say this is a scenario where I could graph out of les standard form with intercepts. So I want to graph this as if the boundary line, as if it says 5x plus 10y equals 40. So as far as x-intercept goes, divide by 5, you get an x-intercept of 8. You get a y-intercept of 4 when you divide by 10. So 8 and 4, keep those in mind when we graph those. plot those 2 points, and we'll go to work. So x-intercept of 8, y-intercept of 4, draw the line through there. Will it be solid or dashed? Well, it can't also be equal to, so I will dash this thing up. For yourself, if you use a pencil, when you draw this line, go ahead and start using the eraser. Or as you have the ruler set on that thing, just draw the dashes as you go if you anticipate it beforehand. Me, I use the line tool and change my setting, because I can. Now, this says less than. Does that mean we shade below? Maybe. I would test 0, 0 in a case like this because y is not by itself. You're not comparing y heights to them. You're comparing this 5x and 10y. So plug in 0, 0, you get a statement that says 0 is less than 40, which is true. 0, 0 is on this side of the equation, therefore everything of the boundary line. Therefore, everything on this side of the boundary line will be true. So yes, it does look like we're going to be shading below. Not always the case with the original inequality that way, but by a test of 0, 0, it does seem to pan out. So I'll do the shading like so. Just do a light shading for yourself in pencil. That'll help for when we hit section 5.7, which is coming up next. Okay, those are 3 out of section 5.6. 5.7 is more of the same when it comes to inequality bits, but we're doing systems. Systems does mean we're going to graph 2 of them together on the same set of axes. They have a solution set potentially, maybe no solution. That's all possible. But we can see it in this example right here. In this example, we see y is less than x minus 2 and y is greater than or equal to 2x minus 4 together on the same pair of axes. You can tell which one's which because, well, did they color code it? No. You can tell which one's which because a solid line versus a dashed line, on which that's dashed and that's solid. And as this line is red, the shaded region above it's red because, well, y is greater than, we shade above. This dashed line we shade underneath because, well, it's dashed there. But we have the purple shaded region is the overlapping shaded region of both of those. What is above the red line but below the blue line is a solution to the system of inequalities, such as a point like 0, -3 would be one of the infinite number of solutions that would exist here. Now, it doesn't seem that we're doing any word problems on these, which would have been my favorite ones to look at and do. I would have done 3 word problems instead of these ones. But in those ones, we really get to talk in real-life context and what happens. But yes, anything within the overlapping shaded region of both of these is considered to be a solution, including points that are on a solid line that bound the overlapping shaded region. So this part of the red also counts, any point there, not on the dashed here. So let's go ahead and it says find the intersection of the half planes, and here's a solution. I don't know if we're required to put a solution. There it is. Okay, number 20 has a system that states y is less than or equal to x minus 3 and y is greater than or equal to x plus 1. Automatically, it looks like we actually might be running into a special case here because these are parallel lines. Now, parallel lines here does not guarantee no solution. It could be, and in all likelihood for this problem, it is. But, and I'm going to do one blue and one green. So slope of 1, as we would also shade underneath this one. I can tell that we shade underneath because the y's are less than the expression that represents this line that gets you y's for certain x's. So we shade underneath this line. You could also test 0, 0 and see you'll make a false statement out of it. I'm not going to do that right now. This will be a solid line. Thy shading will be underneath. It's a good time to make a point of the fact that sometimes people don't do the shading until the very end. That's up to you. By shading at the very end, I mean find the overlapping shaded region and just shade that. So if I do any shading here, I will darken more so the overlapping shaded region afterward and focus on that. The one is y is greater than or equal to x plus 1. This is a slope of 1 with a y-intercept of 1, and we're going to shade above. And I think that's where you can tell that maybe this is a special case here, because not only are the lines parallel, but we're shading above one and below the other in a case where there is no overlapping shaded region. This is an instance where you have, and you should indicate it as such, because there's no overlapping shaded region, there's never an XY ordered pair that would satisfy the system. Therefore, this is a no solution case. I'll make sure to write that as soon as I make this very pretty and colorful here. You know what I should be doing on these, and I stated it at the time for when I did the section, but I never did it. I should really just black and white this thing out afterward, right? You guys don't get the luxury like that. You guys don't get the luxury of seeing them, you know, all whatever. So maybe I should be doing that as well. In either case, guys, this is no solution. Generally, you don't write out a solution set though, right? The overlapping shaded region shows you all the infinite number of solutions. You can indicate a couple of them. This doesn't have any. Let's see if, I don't think we have no solutions the rest of the way, which is cool. Number 21. Let's see if we can finish by the hour. I'm almost there. Number 21, I have y is greater than negative 2x plus 3, and y is greater than or equal to 1/4 x minus 1. Okay. Graph them and go, right? So I'll start in color. Slope of negative 2. I am greater than, therefore, two things will be true about my boundary line and my shading. Boundary line, ooh, I'm going to make blue, but boundary line will be dashed, not solid. And I will shade above the line such that if you test it, 0, 0 will not work. Y is greater than, therefore we shade above. So I'm going to be above this guy. And yet for the other one, I will also be above. However, it's a different line and a solid line. So for this one, y is greater than or equal to 1/4 x minus 1. Up 1, right 4, a couple times here. Remember, we're not about the point of intersection here, right? It's not about the point of intersection. It's about all of the points that represent solutions. So we don't really have to state anything more, unless they asked what's a solution, things like that. Those are very valid test questions. Is this a solution to the system? Is this a solution? Only things in the overlapping shaded region. Now, what's considered to be the overlapping shaded region? Well, let's draw above this green line because y is greater than. 0, 0 counts, by the way. 0 is indeed greater than or equal to negative 1 if you test it out. But the overlapping shaded region is what's blue and green together in that top right region. Let's see what this looks like in black and white and see if it emphasizes that as being, whoopsie, that as being darker. No, excuse me. All right, let's see. Yeah, it looks a little darker there. See, I didn't do this in the section at the time, but yeah, that's the overlapping shaded region right there. Anything there, like 5, 3, is a solution to that system. I should be black and whiting that significantly more often. I don't know why I haven't before. Number 22 is the last question here, and really no different from what we were doing before, so let's just keep it. So, number 22. Now, my top inequality, I'm going to graph out a standard form because, well, I can without fractions. You know what they never had us do in this review set is, and they'll probably do it in the chapter test, but we never had to divide by a negative even when converting to slope-intercept form, which I'll do on the bottom one. So this bottom inequality I'm going to rewrite as y is less than negative 2x plus 7. No, the inequality doesn't flip. In this top one, I got an x-intercept here of 6 and a y-intercept here of 2. And I still got to make sure I test 0, 0, which will fail, which means I won't shade on the side of 0, 0 for that one. So let's go ahead and graph these two. X-intercept of 6, y-intercept of 2. Both of these lines, by the way, will be dashed, so I'm going to go ahead and make them dashed already early on. And I'm not going to shade on the side of 0, 0, therefore I am shading above this here line. So let's get her done. Actually, let's try this. Let's do the lines first, and then let's just consider the overlapping shaded region from there. I did that on a lot of the word problems at the time, so I'll just go and do it here. Negative 2x plus 7 looks like this. That slope's negative. They do intersect right there. That doesn't really matter. Because, here's the thing. The point of intersection actually is not a solution to the system. Because these are dashed lines. Even if one of them was a dashed line, it wouldn't be a solution to the system. This one is a y is less than, therefore we will be shading below that line. So what is above the blue, but below the green as an overlapping shaded region? It would be right, sorry, I'm getting my thing set up for color and such. It would be right here. This would be the overlapping shaded region that is above the blue, yet below the green. Okay, that's what we're looking for as a whole. I have to reduce the size of this thing. It's going to look a little awkward at the end there. There we go. So that is what we should get as our final solution for that one. And guys, that's it. If they said pick an ordered pair that's a solution or something, I could say 0, 5. That would work. 0, 0 is only a solution for the bottom one, not the top one. Things like that, right? It needs to be a solution to the system. Guys, that'll do it for this one. This is Mr. Robinson. Thank you so much for watching. Coming up next after this will be the Chapter 5 test and cumulative assessment. I'm looking forward to that because the mixed review portion means special cases can appear whenever. I can choose whatever method whenever I want, I think, unless they force things on me. I have no idea. And cumulative assessment covers everything from chapters 1 through 5, guys. I'm getting excited for it. I hope you're getting prepped and stoked and ready to go as well. That'll do it for this one. Thank you so much. Take care. I'm going to see you in the next one.